So welcome once again to the water plant and the park here. Part of the design intent for the way that we're configured here with the public park and the plant, there are picture windows that go into the process units as you travel down this sidewalk, and so it's not unusual for us to see people doing this, and we wave, and and if it's little kids, I like to try to come out and talk to them, and I've had some interesting conversations. So just a little bit of an overview as to why this plant was here. The city of Wilsonville was on wells back in the 90s, and we're getting to a point where the wells weren't really providing them with enough water, and so they were under risk of a building moratorium, and the option was to buy water from the city of Portland in the Bull Run or to develop their own source, and it just so happened that a river runs through it, and so there was some water quality studies, and it was determined that the water quality in the Willamette River is actually very fine for drinking water. I like to tell people that the Clean Water Act of 1972 worked, and the surface waters in this country are being cleaned up to an extent, and certainly here in Oregon, we take our water very seriously, and the Willamette is a lovely source. So I understand you're not really here so much about the water quality here at this plant, so you're going to see me kind of race through some of these slides. The river is just down past the tree line down there. We couldn't see it this morning because of the fog, but it's cleared off nicely this afternoon. So once again, just going to kind of cruise through some of these slides. We have three processes here. We have a small footprint, what's called ballasted coagulation and flocculation process. So it just helps us take the dirt out of the water faster. We use chemicals to do that, and we'll have a little discussion about some of the chemicals that we use as we go through the plant. Then we follow that process with ozone. We generate ozone on site from liquid oxygen. Ozone is an O3 molecule generated from an O2 molecule by adding a little energy. Electrical energy gets converted to chemical energy. And then our final step is we have a deep bed granular activated carbon filtration here. My understanding is the plant will have a different filter media than what we use here at our plant, but still filtration. And you'll get a chance to sort of hear or not hear that, such as it is. It's very quiet. So once again, the city of Wilsonville has 4 water tanks that we supply. And we're going to go through sort of the schematics. So as we're walking through the plant, so we have a 320-foot long pipe that extends out into the river. And it brings water into this tank, which is actually mostly below ground. It's the water level in the tank and the river are the same because it's essentially just a big tunnel that connects the two. And then we have our pumps in our raw water facility that pump up to the head of our treatment. And once we're lucky that our site is linear and it goes downhill. So once we've pumped up to the top of the plant, the rest is gravity flow through the plant, and we have our active flow, ozone, and granular activated carbon. Oops, too far. And that goes into our clear well. The clear well extends out under the grassed area down here in the park, so people in the park don't even really notice that they're standing on top of 2.9 million gallons of water.
I got one question. Okay.
Yes, sir.
What size is your intake pipe?
It's 6 feet in diameter.
Okay. Thank you.
Mm-hmm. So before the plant was here, this is what it looked like. It was just an open field. I think it had been used for farming or grazing or what have you. So now we do have the Wilsonville concrete. I don't know if you noticed the sign when you were coming in, is our neighbor on that side, and then there's the subdivision on the opposite side. I don't know, there's no trees in this picture, so all the trees that you see out here have grown up in the last 18 years. So we have some construction photos. This is actually our finished water pipeline, which runs up underneath the water feature and then heads out towards Wilsonville Road. During the construction, in order to get that intake pipe out into the river, they had to put in, this is called a cofferdam. It helps dewater the area where they're working to put the pipe in. And this is something you won't see today because it is underwater. So this is our intake pipe. And on top, you see these fish screens. The next slide is a little bit better view of that. And so there's a 1/16 of an inch mesh on those that, so anything bigger than that can't get drawn into our caisson. So we did find out when we cleaned out the pipe a couple of years ago, however, that clams really like living in our intake pipe. So the pipe is designed for 200 million gallons or so, or could handle that. We typically take in anywhere from 4 to 12. So the water flowing through there is very quiet, and the clams thought that was just great. So when we were cleaning, it gave the divers a bit of a problem. So now the 1/16 of an inch mesh, we have a air burst system, which is a big tank, and we fill it up with air to about 100 psi once a week, and we open the valve, and that's what it looks like out in the river. So we have to make sure that there's no boats out there at the time, because if there was a boat in that area, we would sink it. And we don't want to do that. So Delora would get very upset. She would get calls. Although we thought it would be kind of fun to have maybe a Loch Ness monster come up out of the... So this is the excavation for the clear well. And then putting in the foundation work for that. And you can see the beginning of the, where the pumps, I'm sorry, that's where the support structures sit. So the caisson is an 80-foot, it's 80 feet from the pump deck down to the bottom. So in order to minimize the disruption at the time, they built the concrete in sections at the surface, and then they excavated underneath it with this excavator and sank it down into place. So my understanding is that there's sort of a time-lapse video of that. I haven't seen it myself in the 3 years that I've been here, but try to imagine the man down there in the excavator and excavating underneath that, and that caisson sinking into place. So once the tank section was down, then they began to bore for putting in the intake pipe. And there's the bit. So then on top of that, this is the pump deck going in, the concrete and all the reinforcement. And that's what it looked like 18 years ago. It looks pretty similar to that today. The paint's a little faded maybe, but otherwise. So did we want to go through some more of the treatment process here, or did we want to go ahead and move right on to the tour? A little more of the treatment process? Okay.
If you can, I got just a couple of quick questions.
Sure.
What was the completion date on that plant?
Well, we went into operation in April of 2002.
2002.
So I guess it was completed a few months ahead of that and some testing and things like that. But so there we go. That was what I wanted. So this first step is we're taking out mostly dirt, any particulates, little bugs or what have you. And what we do is we add alum, aluminum sulfate, which I understand is also a chemical that's used for like canning and preserves kind of a thing. So all of the chemicals that we use here are obviously appropriate for drinking water treatment. So they are NSF 61 rated. So they're very safe for consumption. We wouldn't want to go swimming in our chemical tanks just because of the concentration that we have. But everything here from a safety perspective is drinking water rated, and it's obviously not toxic. So we use alum, and what we're trying to do is we're trying to neutralize charges that are in the intake water. And the thing that makes it active flow for us is there's this micro sand particle, and that makes it heavy, so it sinks faster. So it's a more compact process than a conventional clarifier type setup. And so we had this micro sand, and then we had the dirt, and the chemicals are neutralizing the charge, and then we add a polymer, which is kind of like a long string that kind of ties up the package, and it makes this whole thing kind of a sticky flock. And we'll have a chance for you to look and see what that looks like out on our active flow deck. And so we have several mixers mixing the chemical portion, and the polymer and the micro sand actually gets recirculated back through the process. We haven't bought micro sand in years and years. It costs more to ship it here than it does to actually buy the product. So we overflow, and the solids get collected down here in the bottom of this clarifier. The clean water goes up and over into the overflow channel and then on to the ozone process. So we collect the solids on the bottom. They go to another clarifier or a thickener. It's a big round tank. You'll get to see that. And then off of the bottom of that big round tank, we pump into our centrifuges that spin more of the water out. And then the solids, which is essentially dirt for all intents and purposes, we collect that in a couple of roll-off containers. Republic comes and takes that to the landfill and uses it for daily cover material. We do use ozone here. So ozone is a very reactive molecule. It is made from liquid oxygen. We have a liquid oxygen tank on premises. And our ozone generators from the outside just look like big blue boxes. On the inside, we have these pressure vessels. They are water cooled. Inside each of those pressure vessels is 253 glass tubes. And through the glass tube is a braided wire electrode. We run electricity through that electrode past the oxygen that's being fed through, and about 17% of that oxygen is converted to ozone gas. And then the gas then is sent on to our contact basins. The ozone oxygen is bubbled up through the water, and the ozone, being reactive, acts as a disinfectant, but it also breaks up any carbon-based compounds that might be in the water. So we're disinfecting and then also breaking down some carbons. And also the polymer from that active flow process gets broken down, so it gets removed better by the filters. So we have granular activated carbon in our filters here. I understand that you might be using anthracite and other materials. Okay, all right. And so, the reason that we have activated carbon here is that it adsorbs chemicals from the water. And so any additional kind of molecules, whether it be just a metal, some metals or things like that we don't want in the water, But in addition, the breakdown products from the polymer or any other organics that are in the water, those get adsorbed onto the carbon and purify the water, in addition to just the physical filtration process. So we do not have any biological type processes here, so any odors that are associated with the plant would just be maybe a little bit of a chlorine from our chlorine disinfection, or every once in a while you might catch a slight whiff of ozone. But we do quench the ozone at the end of the process. We destroy both the ozone in the water and in the headspace over the contact basins. So this is a typical operation of how we load the filters when we're going to change them out. Every 4 years or so, they come in with a specialized Vector truck and they suck the existing media out and then load the fresh media in. It's all very contained. They did try blowing it in once and there was carbon all over the place, so we learned not to do that. We backwash our filters after 60 hours here, and so that's just taking the clean water from the clear well and then pushing it back up through the filter bed to overflow the particles into our wash water basin that's in the center of the plant. We add sodium hypochlorite here for disinfection, both of the initial disinfection for the water, but we dose so that at the farthest reaches of the distribution center, we've maintained the required disinfection required by the health authority. And that's what the inside of the clear well looks like. Another thing that you won't really get to see today because it's all enclosed. Were there any other questions about the water treatment processes here?
Do you backflush back into the river when you backflush, or is
We backwash into, we have a wash water basin, and from the wash water basin, we repump to the head of the plant. So every drop of water that we pull into the plant leaves this plant as finished water. We have no wastewater stream that's associated really with, that hasn't been finished water before it gets discharged to the wastewater plant. But we don't have a wastewater stream per se.
You mentioned sodium hypochlorite, so you don't use chlorine gas then?
No, we have sodium hypochlorite comes in from HASA up in Longview in tanker trucks. We'll have a chance to go through the chemical room. We have secondary containment on all of our tanks that are volumetrically more than if the tank was full and for some reason it failed.
We also like a stronger version of bleach?
It is bleach. So it is bleach, obviously for drinking water purposes, and it's at a 12.5% concentration. So we dilute it down as part of the treatment process. But it's essentially sort of the same thing as bleach.
how, looking at your infrastructure here and how we came in, how do your trucks get in here with your semis with bringing in?
Same way you came in.
Oh, really?
So we have tankers that bring in the chemicals. There's alum, the sodium hydroxide, and we also have sodium hydroxide for pH adjustment. That's for corrosion control. And so we have the three chemicals: alum, sodium hydroxide, and the sodium hypochlorite. So, and then we also have tanker trucks to bring in the liquid oxygen.
How many deliveries do you get a week?
We get a delivery of any one of those about every 2 to 3 weeks. So we're a 15 MGD plant, and our storage is such that that's about the timing. So I don't think it's particularly disruptive, certainly compared to the Wilsonville concrete trucks that are running in and out all the time. So, are we ready to go see some plant?